So hi everyone. Let's make sure this is live on YouTube. So hi everyone. This is a pre-recorded lecture for Foundation of Data Science today. So we're doing something slightly differently today. My recording studio is a little bit different, but it should still work. So and then if you were not there for the live live recording, so Hassan, the teaching mentor for this, or so the teaching mentee for this class gave the lecture, so I recorded this one ahead of time. So okay, so then there's the quiz today. If you're just watching this, don't forget that that there's a quiz that's going to be on Monday, September 28th. You need to take it by the end of the day. So this lecture won't be as long because of that. So okay, so we want to talk about linear algebra, stuff today, and so we're gonna so we first want to review the concept of rank, right? And so the rank of a matrix, A, which is an n by d matrix, so it can be a square matrix, and like in order to define rank, you have to say talk about these notions of linear dependence. And so if you have these rows, A1, A2 up to AN of A, right? Then you can say you can write some vector D. So each of these AI is going to be in RD, right? And I can say that I can take some Z also in RD, and if I can write Z as the sum I equals 1 to let's just say n from alpha, which is a scalar, alpha I times AI, right? So this guy is going to be a scalar, and so this guy here, so then AI is going to be a vector. Okay, so if I can write another vector Z in this way, then Z is going to be in the span of these rows, A1 up to AN, or we can just say it's in the span of A. So okay, and so if you have this Z, this property, then it's going to be linearly dependent. Then this is what's called linearly dependent on A. So so I can recover the vector Z using the rows of A. Now it could be there are rows I can't recover. There are vectors I can't recover. Those would be then linearly independent. Okay, and so the rank. So just review the rank of A is going to be the maximum, so number of rows which are linearly independent of each other. So okay, so the rank is the maximum of linearly independent rows, and this kind of tells you what the true dimensionality is of the data in the matrix. So if I have rows of each rows is going to be dimension D, then I can have at most D linearly independent rows, even if n is is larger than D. At some point, I can't fit them anymore because remember we drew these pictures of linear dependence, and if I can with any D linearly independent rows, I can recover any vector in the space, right? Any vector in RD. But it could be a case where it's less than that, right? So that's the rank of A, and so the important thing is the rank of a matrix A is going to be less than or equal to the min of N and D, where those are the number of rows and the number of columns. I can define rank exactly the same way with the columns instead of the rows. The maximum number of linearly independent rows are columns that I can choose. If I look at the maximum of linearly independent columns, that also defines the rank. It's always the same way if defined with rows or with columns. So I can use either of those. Okay. So yeah, let's go through this simple example. So an example would be, let's see this matrix A, which is going to be 3, minus 1, minus 7, 2, 2, minus 5. Okay, let's look at this example here. And so let's see, what is the rank of this? Okay, so the rank of A is going to be less than or equal. So this matrix is 2 by 3, so it's less than or equal the minimum of 2 and 3. Okay, so even though there are 3 columns, I can't have a rank of 3 because I only have 2 rows, right? So this is less than or equal than 2, right? So the rank is at most 2. Okay, so I don't have to worry about 3 columns be linearly independent. That can't be possible. So then the rank can either be 1 or 2. So we need to check if the rank is 1, and that's only going to be the case. The rank is 1 if the rows are linearly dependent on each other, which means one row is a multiple of the other. So let's check to see if 3 minus 7, 2, can I write some alpha so that this is equal to minus 1 to minus 5, right? So that if they were linearly dependent, then there would exist some alpha here, and this is our question mark. Can I come up with some alpha? Well, if I did this, then it would, for the first thing to work, it would have to be so it would have to be minus 1/3 if I were to align this guy and this guy here, the first term, the 3 and the minus 1. But then if I multiply minus 1/3 by minus 7, then right by this term, it's going to be a problem. That's not going to give me 2. So these are not linearly independent. So that means the rank has to be 2. There are 2 rows which are linearly independent of each other, so the rank is equal to 2. Okay. Rank is going to be of A is going to be equal to 2. Okay, let's look at another matrix. Call this G. 1, 4, 3, and so 7. This is a 2 by 2 matrix. Okay, so the rank can be at most 2. It could also be 1, but I have the same property that in order to get the second row from the first row, I have to multiply the first coordinate by 4, but then second coordinate, that would give me 12, which is not 7. So the rank of G is going to be also 2. Okay, both of these matrices are example of matrices which are called full rank. So these are full. These matrices are full rank, and that is if the rank of A is equal to the minimum of N and D, right? So if I take the minimum, then there's whichever is smaller, and it's the same for G, but it's different for A. There are only 2 rows, so N is equal to 2. And so all those rows are literally independent of each other. This means it's what's called full rank. Okay, and a square matrix like G can also be full rank. So okay, good. So this is rank of a matrix. So let's get to the main topic of this lecture, which is going to be talking about square matrices. So a square matrix, and these are matrices that aren't often themselves just the same sort of, they don't often represent data the same way a rectangular matrix would, where N and D don't need to be the same. You can have N data points with D attributes, and N and D don't need to be the same. These are matrices. We'll call them the typical matrix we use will be some M as the name of the matrix, and we'll say these are N by N. So this means that it is going to have the same number of rows and so columns. Okay, so this is special sort of matrix that often comes up as some intermediate representation of data or of something else. As we'll see in the, so it can represent properties of data. It could be, or it can come up as like representing the inner products or the distances between them. If you take the Daemine class, you'll see you can represent a lot of graph structure also as a square matrix. I'll just describe them mostly now, and then we'll see instances where these are going to arise pretty commonly. So the first most important thing is we'd like to talk about the inverse of a matrix. Okay, so an inverse is, so we've talked about adding and subtracting matrices, and we've talked about multiplying them, but we haven't talked about like dividing by matrices. And inverse is kind of what allows you to do a division. If you multiply by an inverse, like if I multiply by the inverse of 2, that'd be, so if I multiply by 2 to the minus 1, right? So as like an analogy, if I multiply by 2 to the minus 1, right, then this is equivalent to divide by 2, right? Okay, so if I raise something to the minus 1 power, so the inverse of a matrix will be to raise it to the power minus 1. That's the notation we're going to use. M to the minus 1 is the notation. This is called an inverse operation, and you can only do this. You can only do if M is square and is full rank. Okay, you can only do this operation if it's square and it's full rank. So it has n linearly independent columns. If not, you're kind of doing something like dividing by 0. It's a way of thinking of what happens if it's not full rank, or if it's not square. So we'll later in the semester we'll actually talk about an algorithm to compute the inverse. But in practice, it's something you can call in Python, and you can pretend like it's done exactly, although there is going to be some numerical issues here. Okay, and the property of an inverse of a matrix is going to be that M times its inverse, M so minus 1, is going to be equal to the identity matrix. Okay, and the identity matrix is also an n by n square matrix. This is in our n by n, and it's going to have ones on the diagonal and zeros everywhere else, right? So the first row of this is actually going to look like 1 0 0 0 0 0 1 0 0 0 0. If I there we go, 0 0 1. You know, and it just keeps going down till at the end you have 0 0 0 0 0 1. Okay, so it's going to be this one it's a very special structure. There's only ones on the diagonal of the matrix, and this kind of represents 1. Like if you multiply 2 by 2 to the minus 1, or 2 divided by 2, I get just the scalar 1, and this is the generalization of this for a matrix. So okay, and so because of that, it's also going to be true that the matrix inverse times the matrix is also going to be equal to the identity. This is true on both multiplication on both sides. So okay, so that is the kind of is the property we want of the inverse. It's given a matrix. The inverse is if I multiply it by its inverse, I'm going to get the identity. So that's the definition of what the inverse is doing. And we'll just calculate it in Python in this course. Although at some point we'll talk about an algorithm of computing the inverse of the matrix. We'll do this later on when we talk about principal component analysis and its relation to the to some eigenanalysis as well. So yeah, so okay, so on that track, one way of thinking about this, and another important concept of square matrices are this is like the eigen decomposition. And so this is about the eigenvectors and the eigen values. Okay, so these are eigenvectors and eigenvectors, eigenvalues. This is another important thing about square matrices. So I'm going to have, again, M, which is going to be an n by n matrix. And then, you know, for these, I'm going to have the property where I'm going to have M V. It's going to be equal to lambda V. We typically write it this way, where here, V is going to be a vector in Rn, and lambda is going to be a scalar. Okay, so when we do this, then this vector, we're going to call this vector V is then going to be an eigen vector, and let's see, and so lambda, the scalar, is going to be an eigen value. Okay, so something cool is happening here. Let's look at this equation. We've got a square matrix. So when we multiply it by a vector, it's going to give us back a vector, right? Matrix vector multiplication gives you back a vector. Because it's square, you start with an n-dimensional vector v, and you get back another n-dimensional vector. And what's special about eigenvectors is I basically get back the same vector. The same v is on both sides of the equation here, except for some scale factor that's the eigenvalue. Okay, so this is specifically for any v where this is true. It's often called an eigenvector, but we typically say, you know, the common thing is to make so that v is the norm of v. Let me write this a little bit more clearly. The norm of v, and that's the L2 norm, is going to be equal to 1. Okay, so if I multiplied v by 2, this equation would still work, right? Because I'm multiplying by 2 on so both sides. So it's typical to write if it's just I can pass that scalar through. So that's interesting. So we typically make the eigenvector have a norm 1, so it's a unit vector. So it's a unit. This is the typical thing to do, but even if it's not a unit vector, it's still technically an eigenvector. But the packages you run to create and to find the eigenvectors of a matrix are typically going to give you the unit vectors. So okay, so these are very special special types of vectors. This is not true of like an arbitrary vector. If I have a square matrix and I multiply it by an arbitrary vector, I'm probably not going to get back a scale multiple exactly. This is not typically going to be true. These are very special structures of this, and it's associated with the matrix, right? So given a matrix, an often task is to find, the eigenvectors and the eigenvalues. Matrix always has these, but there's actually going to be a finite number. Okay, and so there's in fact always going to be at most n distinct eigenvectors. So there are at most n distinct so of these eigenvectors and the associated eigenvalues. Each eigenvector is paired with an eigenvalue. Okay, and these tell you a lot of structure about the matrix, which is pretty important. Now, so let's go through a simple example. So let's look at matrix M. Let's see, I've got one worked out. 3, 1, 3, 4 is the first column. 3, 5, 2, 4, 2, 8. Okay, so this is our matrix N. Its square is 3 by 3, right? This is 3 by 3. Okay, and so if you just look at this, it's it's hard to just know offhand what the first eigenvector is, but I pre-calculated this, so I can just write down that the first eigenvector 0, 4, 3, 0, 4, 4, 0, 7, 8. I've rounded this to two digits after the 0. Okay, so this is the first eigenvector. If you check, you square these and add them up, they should add up to 1. So this is actually is a unit vector, and this is associated with the first eigenvalue, which is 11.36. So indeed, the first eigenvalue here is the squared spectral norm, right? This term is going to turn out to be the spectral norm with the strange matrix norm squared. Okay. Okay, so that's the first eigen, and when I say the first one, that's going to be the largest. So the first or the top eigen vector is the one with the largest eigenvalue. Okay, so they're going to be, this matrix is going to have other eigenvectors and eigenvalues, but this is the largest eigenvalue associated with it, right? So this is the eigenvalue, and this will be the largest of all of them. Okay, let's write down the other ones. So V2 is going to be 0.11. Let me write this a bit more clearly. This is minus 0.11, minus 0.83, and 0.54. Okay, this is only unique up to a sign. So I notice they're negative values now. If I flip them all, multiply by -1, it's still going to be a unit vector, and I'm multiplying by -1 on both sides of my equation. So this is still okay. So this is, I can flip the signs on all of these. And the associated eigenvalue here is going to be 4.10, right? So this is smaller than the first one, right? Okay. And then V3 is going to be minus 0.90, 0.31, 0.31. Okay, and the third eigenvalue is going to be negative 0.46. Okay, so these are decreasing in magnitude, and something kind of maybe odd is happening. You're seeing this eigenvalue can be negative as well. This turns out that in fact the eigenvalues could be negative. They could be they could even be they can even be complex numbers. Okay, when this happens, it's kind of strange to interpret what's going on. So in this class, we're basically going to only, other than this example, we're only going to work with matrices that have all positive or at least all non-negative and real eigenvalues. Okay, so in this class, and in a lot of data analysis, eigenvalues in this class will have so each lambda I is going to be real and so positive, or zero. Okay, so I'll be real, they'll all be positive, or there'll be some cases where they'll be zero, and we'll explain this in a bit. So this will simplify things, and when we talk about the relation to principal component analysis, this will be a much closer link or to the singular value decomposition later. So hopefully a lot of you have heard of kind of eigenvalues and eigendecomposition in the past. We'll just mention them, but we'll mainly talk about the SVD later in class, and I won't define that today. We'll spend at least a whole lecture just talking about how to interpret that. Okay, so when we talk about, so if I have a square, so matrix M, okay, with n positive and real, so eigenvalues, then that means it's this condition called positive so semi-definite. Okay, so then it's called positive definite matrix. Okay, so if it has all real and positive eigenvalues and it's square, then this is what's called positive definite. Okay, and the example we had on M was not positive definite because on the previous slide, because one of the eigenvalues was negative. So that's not positive definite. There's also called, so if the eigenvalues are real and negative, so we could have some values which are zero. They can't go negative, but they have to be, but they could be zero. Then that's called positive semi-definite. Okay, so these are kind of these are the matrices where it'll make sense to interpret the eigenvalues in a lot of very, very convenient ways. And so we will construct matrices. I mentioned these square matrices are usually an intermediate representation of the data. And so we'll construct them in a way so that they have these properties. So we'll typically know that they will have these properties, and then we don't have to worry about, in this class at least, dealing with the negative or the complex eigenvalues and what those mean. Okay, and so typical way of doing that is if I have a matrix A, which is in n by d, then I can set M to be equal to A times A transpose, right? If I do it by A transpose, so then A is an n by d matrix, A transpose is going to be a d by n matrix, so the result is going to be an n by n matrix, okay? And if I construct it this way, it has, and all the entries of A are real, right? It's in R to the ND, then it's going to be positive semi-definite. If it's constructed in this way, it must be so positive, so semi-definite. Okay. And if it's constructed in this way and it's full rank, then it has to be positive definite. If M also full rank, then it's going to be positive definite. Okay, so the rank of matrices are kind of, it's so if for instance, if A is rank n, okay, so that would have to be n is less than d in this case. If A is rank n, then M will also be full rank. It'll also be rank n, and it will be positive definite. If A is rank d instead of n, right, or smaller than d, then it will end up being positive semi-definite. Okay, so that's way where we know based on our original data whether this is going to be a positive definite or positive semi-definite matrix M once we've created in this way by A transpose, or you could do A transpose A. That's works just as well, because if you take a transpose twice, you get back the original matrix. Okay, if I did A transpose A, then it would be D by D matrix M. Okay, so I can consider both of these, and we'll talk about these in context later in the semester. Okay, the other property of positive semi-definite matrices, so they also, let me just get it on the same slide, have, if you have X that is going to be in Rn, this is some vector, okay? Then we're going to have the property that X transpose MX is going to be greater or equal to 0. And if it's positive definite, it's always greater than 0. If it's positive semi-definite, it might be 0. Okay, so this is what's weird about this, is for all vectors X. So for any vector X, I multiply by M on both sides, by X on one side, by X transpose on the other side, right? So I think I do X times M, I get a vector of the same dimension as X, and I do times X transpose again, I'm basically taking the dot product, right? And so it's back a scalar value, and this will always be positive for any vector X. The first time I heard this, I'm like, how can you possibly do that? What if I put a minus sign inside the X? Isn't that going to make it so it's negative? Can I change it with the minus sign? And that's the answer is no. These things exist, and the way to think about it is that it's like you've squared something, right? Think of M as A transpose. So I've done X times A transpose, and I've gotten a vector. And then on the other side, this is basically, think about this as X transpose A transpose X, right? So I can decompose the order I do these operations. And so I'm basically getting this vector. One is the transpose of the other one. And I'm taking the dot product with itself. Okay, so and so that's why it's positive. When you take a dot product with itself, you're kind of like squaring something. So if I take a negative number and I square it, it's going to be positive again. And that's what's going on here. Every term in this dot product is going to be the same, and I'm squaring all those terms and then adding them up. So that's why it's positive if the matrix is positive definite, or so positive semi-definite could be 0 exactly if you pick the vector just right. Yeah. So okay. So that's positive definite matrices have all positive eigenvalues, right? And you can also think of it as satisfying this property. For every vector x, I multiply it on both sides, and I'm going to get a positive value. Okay, and I can construct these with A transpose A. If long as the A is a real matrix, I can construct these positive definite, these matrices. So okay, there's one more. So yeah, so there's one more concept I want to cover in the lecture today, is orthogonality. Okay, and so this is yeah, so the idea of this is something that you define over vectors, but then if you define it over vectors that's satisfied within the vectors that make up a matrix, you'll define for a matrix as well. And this will relate actually to the eigenvectors as well. We'll come back to it. There's another property of those which I will say with respect to orthogonality. Okay, so let's define this for two vectors, x and y in Rd. Okay, so I have two vectors, x and y. And if x dot y is equal to exactly 0, then we say that x and y are orthogonal. Okay, so they have to equal to exactly 0 in the dot product of each other. Okay, so this is the technical definition. The way to think about this with vectors in geometry, I always like kind of the geometric intuition, is that if you have one vector x here, and you have another vector y, right here, then they are orthogonal as long as this is a right angle. This is exactly 90 degrees between them. Okay, and this works in two-dimensional space, right? So, example in two-dimensional space would be, let's say this is 4, 1, and then this one would, if I drew it correctly, which it's a little bit off here on the grid, but then this would have to be equal to -1, 4. Then these would be orthogonal with each other. Okay, and let's just check this out. If I do this, so if I do this dot product together, so for 1 dot product with -1, 4, right? This is going to be -4 plus 4, that's equal to 0. Okay, so you can, in the plane, you can switch the role of the digits and put a negative sign on one of them. That's the only way you can get orthogonal vectors in the well, you can also make it longer. If I made y twice as long, it would so they would yeah, what's gonna is, yeah, if I'm, let's see, if I made y twice as long here, let's just do this on the spot. Let's make y go out here, and so then this would be -2, 8. What's going to happen here? So I'm going to have for 1 dot product with -2, 8. What's going to happen? I'm going to get -8 plus 8. This is still 0, right? So if I multiply it by 2, they're still going to be orthogonal with each other. It doesn't matter the scale here, it just matters the angle in between these vectors. Okay. So this intuition, even though I've drawn it in the plane here, this works in any high dimensional space as well. This intuition that the angle has to be exactly 90 degrees for them to be orthogonal. And how does that work? Can we define an angle in high dimensions? The answer is yes. You can always just look at the subspace that goes through those. So I have stuff in my, in this three-dimensional space here, but I have two vectors, and those two vectors and the origin lie in some two-dimensional space, and there I can measure angles, right? And you can, and so if that angle is 90 degrees, then they are going to be orthogonal to each other. Let's go through a slightly longer example. Let's check if this x2 minus 3, 4, minus 1, 6, if this is orthogonal to y. This example I wrote down in my notes, and minus 2. So let's see if this is going to be orthogonal. We can add these up. 8 minus 8. We're gonna let's just plus 7. I'm just doing this kind of element wise. Plus 7. Okay, and then this one is minus 12. So the ultimate result of this is minus 12. So these are not going to be orthogonal with each other. Okay, if I have vectors and I don't know anything about them, and I want to know if they're orthogonal, I just need to take the dot product and check if it's exactly 0. Oh wait, no, this was 3 times. I messed up here. This is without a live audience, I can more likely make a mistake. This is 3. That's minus 15. This is 3. See, this is plus 12. Okay. Now let's see if I did this correctly. You get 2 examples for the price of 1. Well, if I add all of these things up, I'm going to get exactly 0, and these are going to be orthogonal. Good. Okay, so these vectors are orthogonal because the dot product is going to be 0, and that's what it means. So this is for vector orthogonality, but for matrices, I can also I want to say if a matrix is orthogonal, a matrix V, well, V is a common thing to use, n times d. So if it's v by if it's n by d, and has all, let's see, so this is if let's and all orthonormal orthogonal so rows, or let's say so columns, and they're all unit vectors. Okay, so V is equal to V1, V2, up to Vd. And if each of these VIs is equal to 1, and Vi dot Vj is equal to 0, then this is called orthonormal. Then this matrix is called orthonormal. Okay, so if we have a and then if we have a square matrix U, u in R n times n, and all and if I then have all orthogonal rows and so columns, then I'm going to say that this is an orthogonal matrix. Okay, so then I have an orthogonal matrix. If it is a square matrix and I have all these orthogonal rows and columns. So these should also the rows and so columns should be so unit vectors. Yeah, so usually this has been normalized. Okay, so if this is the case, what's going to happen? So if I have an orthogonal so matrix U in R n n by n, then I'm going to have the property that U transpose is going to be the identity matrix, right? So I'm going to get the identity matrix, and the reason why is that, well, this is because each row or column UI dot UI, right, is going to be 1 because this is equal to the norm of UI squared. If I look at the norm, the two norms squared, well, that's the same as the dot product with itself. So that's going to be 1. So and I do a matrix multiply, the element that's on the diagonal of the matrix is going to be a vector dotted with itself, where everything off that's not on the diagonal, so UI and UJ, that's going to be 0, right? So this identity matrix, remember, is 1s along the diagonal and 0s everywhere else. So everyone, this is here, this corresponds with matrix by itself, and everything, each of the kind of the 0s that's off the diagonal, right? One of these guys, 0s, that corresponds with an I and a J with each other that aren't the same. So that's why with an orthogonal matrix, you're going to get U times U transpose is going to be its identity, which means that U transpose is equal to the inverse of U. So if I have an orthogonal matrix, I know how to take the inverse. Okay, so this is a special case. If we can have an orthogonal matrix, then it's going to have an inverse. Yeah, so one property, so let's go back to the eigenvectors of a matrix. Let me just say one thing about these. These must be orthogonal, right? So if I have M, remember, VI equals VI lambda, I have M Vj equals Vj lambda, then Vi dot Vj is equal to 0 if Vi is not equal to Vj. Okay, so this is another property of these eigenvectors, in that they're going to be orthogonal to each other. So if we can find the eigenvectors, we're finding this orthogonal basis of the span of data that can be represented by this matrix M. So if I have a basis, remember, a basis is a set of vectors which is enough to describe the linear dependence structure, right? So I can recover any other vector by multiplying by scalars of these vectors, and this is going to be this is the basis, and I have an orthogonal basis if all the vectors in that are going to be going to be orthogonal to each other. And again, the most common orthogonal basis is exactly going to be just the coordinate axes, right? So 1, 0, and 0, 1. If I take the dot product with those, it's 0, right? So this gives me an orthogonal basis, but I can have a different basis as well. I could say this is V1 and this is V2. This gives me a different orthogonal basis of the space, just a rotation of the space. Okay, and we'll come back to an interpretation of these. Other properties of orthogonal, so matrices, they basically have no scale information. Okay, so that means that for any vector x and n, let's say in Rn and n orthogonal matrix M in Rn by n, then the norm of x is going to be equal to m, the norm of m times x. Okay, so if I multiply x by an orthogonal matrix, I'm not changing the norm, I'm just changing, I'm not changing the scale of x. The resulting vector I get, let's call this a vector y, it's going to have the same length as I had before. It doesn't change the scale. So this is because I'm basically just describing a different basis, and I'm basically writing this vector in this basis. Okay. Right, so I can think of this as a rotation of the space. Okay, so if I have this original, data here, I've got some point x, and I've got some, and it currently has this coordinate, let's call this 5, 2, and I've got a new orthogonal basis here. Let's call this V1 and V2. Okay, then when I take the dot product, I'm basically going to be projecting it onto here and onto here. I'm getting two new vectors here. So this is going to be V1, V1 dot x. That's going to be that length, and in this coordinate system. And this is going to be V2 dot x, right? And so this is going to be about, let's say this is -2, and this one is going to be 5. And so it's not always going to be the same coordinates like this. I just picked numbers which are easy, but it's going to be the same length. I haven't changed the length. You can have things which are negative. That's fine, but the length is going to be the same. So I can think of this as a rotation of the coordinate system. I've changed the y-axis to v1, or the y-axis to v2, the x-axis to v1, and I've kind of rotated it from one side to the other. And that's all I've done. I can think of taking this point, and there's a new basis here, v1, v2, and then now this point x is going to be 5 and -2 here, right? Or maybe it's out further if those are unit vectors. This is going to be this V matrix times x is going to be out here if these are the coordinates of the V matrix, right? So there's a new coordinate system here, and I've just written this in the new coordinate system, and it's just the rotation here, right? If I take that thing ahead and I rotate it, so that's the new coordinate system that I'm just writing in that coordinate system. So that's what orthogonal matrices are doing. Think of it as a rotation of the space, although if it has some signs in there, it can be a sign flip as well in addition to a rotation. So great, so this is what I wanted to cover. These are kind of very useful properties in linear algebra. Starting the next lecture with linear regression, and then especially with dimensional reduction, we're going to use all these things pretty heavily to actually do some data analysis. But let's stop there. And yeah, feel free to kind of, even though yeah, so and don't forget your quiz is happening today if you're watching this on the day it's posted.